Hello and welcome to the Sleepy Oceanographer. If you're settling in for the night or simply looking for something calm and quietly fascinating to drift away with, you've found exactly the right place. Before we begin, if you enjoy this channel, please consider subscribing and leaving a comment. We'd love to know where in the world you're watching from tonight, and whether you're listening in bed, on the couch, or somewhere else entirely. Wherever you are, we're glad you're here. Tonight, we're going to follow the ocean's invisible rivers. Not rivers in the way we usually think of them. No banks, no clearly defined channels, no water you could step into from a muddy shore, but rivers nonetheless. Vast, slow, enormously powerful movements of water that circle the entire planet, carrying heat from the equator toward the poles, drawing cold water up from the deep, and quietly shaping the climate that every living thing on Earth depends upon. These are ocean currents, and though they are largely invisible to the eye, moving slowly enough that you would never feel them from the surface of the sea, they are among the most consequential forces on our planet. They decide where rain falls. They moderate temperatures along entire coastlines. They feed the fisheries that billions of people rely on. They have shaped the routes of explorers and the fates of empires. And they are connected, through a system of breathtaking complexity and elegance, into a single planetary circulation that oceanographers have spent centuries trying to fully understand. We will travel through all of it tonight. We will begin with the simplest currents, those driven by the wind at the ocean's surface, and then descend, slowly and quietly, into the deep circulation driven by temperature and salt, the great conveyor belt that moves water around the entire globe on a journey measured not in days or years, but in centuries and millennia. We will visit specific currents that have shaped history, explore the science of how they form and what sustains them, and consider what happens when they are disturbed. There is no need to rush. The ocean has been circulating for hundreds of millions of years. It will continue long after any of us are here to observe it. So breathe slowly, let your body relax, and allow the currents to carry you gently along. To understand ocean currents, it helps to start with a simple question that turns out to have a beautifully complex answer. Why does the ocean move at all? The ocean is not a still body of water. It is never truly at rest. Even in its calmest, most placid moments, it is in constant motion, stirred by forces operating at every scale from the microscopic to the planetary. Waves move at the surface. Tides pulse in and out with the gravity of the moon and the sun. And beneath all of that, great rivers of water flow continuously, driven by forces that have nothing to do with the weather on any particular day, and everything to do with the fundamental physics of a planet that receives heat unevenly and rotates on its axis. The most immediate driver of surface ocean currents is the wind. When wind blows consistently across the surface of the ocean, it drags the water beneath it along with it. This is not an instantaneous transfer. The relationship between wind and water is a gradual one, built through friction at the interface between the moving air and the ocean surface. But given enough time and enough fetch, which is the distance over which the wind blows unobstructed, this friction sets the surface water in motion. The connection between wind and water runs deeper than you might expect. As the surface layer of water is set in motion, it drags the layer beneath it, and that layer drags the one beneath it, and so on downward. But each successive layer moves more slowly than the one above it, and each one is deflected slightly to the side relative to the layer above. This deflection is caused by the rotation of the Earth, a phenomenon called the Coriolis effect, which we will spend some time with shortly. The result is a spiral of current direction with depth, a structure called the Ekman spiral, after the Swedish oceanographer Van Wolfrid Ekman, who first described it mathematically in the early 20th century. The net result of this spiral is that the average flow of water in the wind-driven layer is not in the direction the wind is blowing but roughly perpendicular to it. In the northern hemisphere, the net flow is 90 degrees to the right of the wind direction. In the southern hemisphere, it is 90 degrees to the left. This perpendicular flow has enormous consequences for where water accumulates and where it is drawn away from the surface, consequences that affect fisheries, climate, and the distribution of nutrients across the global ocean. But wind is only part of the story. There is a second driver of ocean circulation that operates at greater depths and on longer timescales, and it is driven not by the atmosphere pushing on the surface of the ocean from above, but by differences in the density of the water itself. Seawater is not uniform. Its density varies depending on two key properties, temperature and salinity. Cold water is denser than warm water. Saltier water is denser than fresher water. When water becomes dense enough, it sinks. When it is less dense than the water around it, it rises. These vertical movements, combined with horizontal flows that respond to pressure differences created by density variations, generate what oceanographers call thermohaline circulation, from the Greek words for heat and salt. Thermohaline circulation operates over vastly longer timescales than wind-driven circulation. The surface currents respond to changes in wind patterns over days and weeks. The deep thermohaline circulation carries water that may not have touched the surface for 1,000 years or more, following pathways that wind slowly through every ocean basin before eventually returning to the surface somewhere else on the planet. Together, these two systems, the wind-driven surface circulation and the density-driven deep circulation, create the full architecture of ocean movement. They are not independent. They interact and exchange water at their boundaries, and they are both essential to maintaining the conditions that make Earth habitable. Before we can follow the major ocean currents, we need to understand one of the most elegant and counterintuitive phenomena in all of Earth science, the Coriolis effect. The Earth rotates from west to east. At the equator, the surface of the planet is moving eastward at roughly 1,670 kilometers per hour relative to the axis of rotation. At higher latitudes, the surface moves more slowly because the circumference of the circle traced by each point on the surface decreases as you move toward the poles. At the poles themselves, the surface is barely moving at all in terms of eastward velocity. It is simply spinning slowly in place. This variation in rotational speed with latitude has a profound effect on anything that moves across the surface of the Earth, whether that thing is a parcel of air, a stream of water, a missile, or any other object moving freely over long distances. To an observer standing on the rotating Earth, any such moving object appears to curve. In the northern hemisphere, it curves to the right. In the southern hemisphere, it curves to the left. This apparent deflection is the Coriolis effect. It is important to understand that the Coriolis effect is not a real force in the sense that gravity or friction are real forces. It is a consequence of the rotating reference frame from which we observe motion. If you could watch the moving object from a fixed point in space, not rotating with the Earth, you would see it moving in a straight line. It is only from the perspective of someone rotating with the planet that the path appears curved. But that apparent curvature has very real consequences for the circulation of both the atmosphere and the ocean. The Coriolis effect is responsible for one of the most recognizable features of the global ocean, the Great Subtropical Gyres. A gyre is a large, roughly circular system of ocean currents. There are 5 major subtropical gyres, one in the North Atlantic, one in the South Atlantic, one in the North Pacific, one in the South Pacific, and one in the Indian Ocean. Each of them rotates clockwise in the northern hemisphere and counterclockwise in the southern hemisphere, driven by the combination of prevailing winds and the Coriolis deflection. The mechanism behind gyre formation involves a beautifully elegant balance of forces. The trade winds near the equator blow westward, pushing surface water toward the west. The westerly winds at higher latitudes blow eastward, pushing surface water toward the east. These opposing wind stresses push water toward the center of each gyre, creating a subtle mound of water at the middle that is actually slightly higher than the water at the edges. The Coriolis effect then deflects the water flowing outward from this mound, causing it to curve and sustaining the circular motion. The result is a system of connected currents flowing around the perimeter of each gyre. These currents have names and characters of their own, and they have played enormous roles in human history, in the distribution of marine life, and in the regulation of climate. We will spend considerable time with several of them. One feature of gyre circulation that deserves special mention is the asymmetry between the western and eastern sides of each gyre. The currents on the western sides of the ocean basins, where the gyres flow poleward, are narrow, fast, and deep. The currents on the eastern sides, where the gyres flow equatorward, are broad, slow, and shallow. This asymmetry arises from a complex interplay between the Coriolis effect and the variation of that effect with latitude, a phenomenon captured in what oceanographers call the beta effect. The fast western boundary currents include some of the most powerful and consequential flows in the ocean: the Gulf Stream in the North Atlantic, the Kuroshio in the North Pacific, the Brazil Current in the South Atlantic, the Agulhas Current in the Indian Ocean. Each of these currents carries enormous volumes of warm water poleward, releasing heat to the atmosphere and profoundly influencing the climates of the regions they pass. Slower eastern boundary currents have a different but equally important character. Because they flow equatorward along the eastern edges of ocean basins, and because the Ekman spiral causes net water movement away from the coastline in these regions, cold deep water is pulled upward to replace it. This process, called coastal upwelling, brings nutrient-rich water from the deep ocean to the surface, fueling explosive growth of phytoplankton and supporting some of the richest fisheries in the world. Of all the ocean currents on Earth, none has captured the human imagination more fully or shaped human history more directly than the Gulf Stream. It is one of the most powerful ocean currents on the planet, a river of warm water flowing northward through the western North Atlantic at speeds that can exceed 8 kilometers per hour at its core, carrying a volume of water roughly 50 times greater than all the rivers on Earth combined. The Gulf Stream originates in the Gulf of Mexico, where warm tropical water accumulates under the relentless heating of the tropical sun. This warm water flows out through the Straits of Florida, squeezed between the tip of Florida and the Bahamas into a narrow, fast-moving jet. It then turns northward, hugging the eastern coast of the United States before eventually separating from the coast somewhere around Cape Hatteras, North Carolina, and swinging out into the open Atlantic. From Cape Hatteras, the Gulf Stream flows northeast across the Atlantic, gradually broadening and slowing as it goes. By the time it reaches the waters south of Iceland and Greenland, it has transformed from a tight, fast jet into a broader, slower drift, releasing enormous quantities of heat to the atmosphere above. This heat release is what gives northwestern Europe its disproportionately mild climate. London, at roughly the same latitude as Calgary, has winters that would be unrecognizable to someone from the Canadian prairies. Bergen, on the Norwegian coast, sits at the same latitude as southern Alaska, but maintains ice-free harbors year-round. The Gulf Stream was known to the indigenous peoples of North America long before Europeans arrived on the continent, and it played a crucial role in the early history of transatlantic navigation. Spanish ships returning from the Americas in the 16th century discovered that by sailing northward along the Florida coast and catching the current, they could reduce their return crossing time dramatically. The current carried them northeast and then, with the prevailing westerlies, back across the Atlantic to Europe, far faster than a direct route would have allowed. Benjamin Franklin, who served as Deputy Postmaster General of the American colonies, became interested in the Gulf Stream in the 1760s when it was noted that British mail packets were taking 2 weeks longer than American merchant ships to cross from England to America. Franklin consulted his cousin Timothy Folger, a Nantucket whaling captain with extensive practical knowledge of the current, and produced the first printed map of the Gulf Stream in 1769. The map showed the course of the current and advised captains crossing from England to head south to avoid it, advice that the British Postal Service reportedly ignored. The scientific study of the Gulf Stream accelerated dramatically in the 19th and 20th centuries. Matthew Fontaine Maury, an American naval officer and oceanographer, compiled thousands of ships' logs to produce detailed charts of winds and currents, including the Gulf Stream, that transformed navigation and earned him the title of the father of modern oceanography. Subsequent work using ever more sophisticated instruments revealed the Gulf Stream to be far more complex than the simple river Franklin had mapped. It meanders in great serpentine curves, occasionally pinching off warm and cold eddies that spin away from the main current and persist for months. It carries not just warm surface water, but a complex structure of temperature and salinity extending hundreds of meters deep. The volume of water transporting by the Gulf Stream is almost incomprehensible in its scale. At its narrowest point in the Florida Straits, it moves approximately 30 million cubic meters of water per second, a figure that oceanographers express as 30 Sverdrups after the Norwegian oceanographer Harald Sverdrup. One Sverdrup is 1 million cubic meters per second. By the time the Gulf Stream reaches its widest extent in the North Atlantic, its transport has increased to around 150 Sverdrups as it entrains additional water from the surrounding ocean. The Amazon River, the largest river on land, carries about 0.2 Sverdrups. The entire discharge of all the world's rivers combined amounts to roughly 1 Sverdrup. The temperature contrast between the Gulf Stream and the surrounding ocean creates one of the sharpest thermal boundaries in the ocean. On one side of the current's western edge, waters may be 20 degrees Celsius. On the other side, just a few kilometers away, the temperature may drop to 5 degrees. This boundary, called the Cold Wall, was well known to fishermen and mariners long before it was scientifically described. Fog forms readily along the Cold Wall as warm, moist air from over the Gulf Stream meets the colder water on either side. The Gulf Stream does not flow forever. As it releases heat in the North Atlantic and its waters cool, they eventually become dense enough to sink, contributing to the deep circulation that carries water away from the surface and into the interior of the ocean. This sinking is the final stage of the process that begins in the tropics and ends in the cold waters south of Greenland and Iceland. It links the Gulf Stream to the global thermohaline circulation, making it not just a regional phenomenon, but an essential component of the planetary system. The North Pacific has its own western boundary current, a counterpart to the Gulf Stream in both its power and its influence. The Kuroshio, whose name in Japanese means black current, flows northward along the eastern coast of the Philippines and Taiwan before turning northeast along Japan's Pacific coast. It is one of the strongest ocean currents in the world, carrying water at speeds comparable to the Gulf Stream and transporting volumes of warm tropical water that fundamentally shape the climate of Japan, Korea, and the broader North Pacific region. The name black current refers to the dark indigo-blue color of the Kuroshio's water, which contrasts visibly with the greener coastal waters it flows beside. This color difference reflects the Kuroshio's origins in the subtropical Pacific, where the water is warm, clear, and oligotrophic, meaning it contains relatively few nutrients, and therefore supports only sparse populations of the phytoplankton that give coastal and temperate ocean waters their greenish hue. The Kuroshio is a beautiful and somewhat barren current, carrying heat efficiently northward, but offering relatively little in the way of marine productivity along its core. Like the Gulf Stream, the Kuroshio eventually separates from the coast and flows eastward across the Pacific as the Kuroshio Extension, a broad, complex system of meandering jets and eddies that transitions into the North Pacific Current. This eastward flow carries the heat accumulated in the tropics across the entire Pacific Basin, eventually releasing it to the atmosphere and contributing to the mild, wet climate of the Pacific Northwest coast of North America. The North Pacific Gyre that the Kuroshio is part of differs from the North Atlantic Gyre in one significant way that has become impossible to ignore in recent decades. At its center, in the relatively stable region where the gyre's currents converge and there is little net flow, the ocean has accumulated an extraordinary concentration of plastic debris. This accumulation, often referred to as the Great Pacific Garbage Patch, is not a solid island of trash, but a diffuse region of elevated plastic concentration, extending over an area that some estimates place at twice the size of Texas. The physics that creates this accumulation are the same physics that drives the gyre itself. The Ekman transport pushes surface water toward the center of the gyre from all directions. Any floating debris caught in this flow is eventually transporting to the central region and held there, because the slow, sluggish circulation at the gyre's heart provides no efficient pathway for escape. The plastic that accumulates here has entered the ocean from rivers, coastlines, and shipping routes, and it persists because most of the synthetic materials of which it is composed do not biodegrade on any timescale relevant to human planning. The South Pacific Gyre, the largest of the 5 subtropical gyres, rotates counterclockwise and is bounded on its western side by the East Australian Current. This current flows southward along the coast of eastern Australia, carrying warm tropical water from the Coral Sea down toward New South Wales and Victoria. Like the Gulf Stream and the Kuroshio, the East Australian Current is a western boundary current, narrow and fast on its western side, releasing warm water and heat into a region that would otherwise be considerably cooler. The Tasman Sea, enclosed between Australia and New Zealand, receives water from the East Australian Current as it flows south and then east. The oceanography of the Tasman Sea is complex and dynamic, marked by a series of large eddies that spin off from the main current and persist for months, carrying warm tropical water far south of its usual range. Marine biologists have documented how these warm core eddies can transport tropical fish species and other organisms into waters where they are not normally found, providing a preview of what sustained warming might mean for the marine ecosystems of the southern Pacific. While the western boundary currents command attention through their sheer power and their influence on climate, the eastern boundary currents play a role in the ocean's ecology that is arguably even more important per unit of volume. These are the currents that bring the deep ocean to life at the surface. The California Current flows southward along the western coast of North America, from roughly the latitude of British Columbia to the tip of Baja California. It is a broad, slow, cool current, the eastern edge of the North Pacific Gyre's clockwise circulation. As it flows southward, the Ekman spiral causes the net water movement to be directed offshore, away from the coast. This offshore movement of surface water creates a deficit that must be filled from below, drawing cold, dense, nutrient-rich water up from depths of a few hundred meters. This process, coastal upwelling, is what makes the waters off California and Oregon so extraordinarily productive. The deep water drawn to the surface is rich in the dissolved nutrients that phytoplankton need to grow, nutrients that have accumulated over centuries from the slow decomposition of organic matter sinking from the surface. When this water reaches the sunlit zone, phytoplankton populations explode. They are eaten by zooplankton, which are eaten by anchovies and sardines, which are eaten by larger fish, seabirds, and marine mammals. The food web built on this upwelling supports some of the world's most important fisheries. The Humboldt Current, also known as the Peru Current, performs the same function along the western coast of South America. Flowing northward from the tip of Chile to the equator, it is one of the world's most productive eastern boundary currents. The cold, nutrient-rich water it upwells along the coasts of Peru and Chile supports enormous populations of anchoveta, a small fish that is processed into fish meal and fish oil and exported around the world as animal feed. At peak productivity, the Peruvian anchoveta fishery was for several decades the largest single-species fishery in the world by catch volume. The Benguela Current off the west coast of southern Africa and the Canary Current off the northwest coast of Africa complete the pattern. Each is the eastern boundary current of its respective subtropical gyre, each drives coastal upwelling, and each supports rich marine ecosystems and important fisheries. The Benguela is particularly notable for supporting the breeding colonies of African penguins, species that have adapted to surprisingly warm continental conditions, by relying on the cold, productive Benguela waters for their food. The seasonal pattern of upwelling varies along each of these coasts. In California, upwelling is strongest in spring and summer, when the prevailing winds blow most consistently from the north, maximizing the Ekman transport offshore. In autumn and winter, the winds weaken and often reverse, and upwelling slows or ceases. During these seasons, the water along the California coast warms, and a completely different set of organisms dominates the nearshore community. Understanding upwelling is essential to understanding one of the most powerful climate phenomena in the Pacific, El Niño. Under normal conditions in the tropical Pacific, the trade winds blow consistently from east to west along the equator, driven by the temperature difference between the cool eastern Pacific and the warm western Pacific. These winds push warm surface water westward, piling it up near Indonesia and the western Pacific in a phenomenon called the warm pool. Meanwhile, in the eastern Pacific near Peru and Ecuador, upwelling of cold, deep water keeps the surface cool. This arrangement is self-reinforcing. The temperature contrast between the warm west and the cool east drives the trade winds, and the trade winds maintain the temperature contrast. It is a coupled system, ocean and atmosphere locked together in a stable configuration that has prevailed for most of recorded history. But every few years, this system loses its grip. The trade winds weaken. The warm water in the western Pacific warm pool begins to slosh back eastward, spreading across the central and eastern equatorial Pacific. The upwelling of cold water off Peru is suppressed as the warm surface layer deepens. Sea surface temperatures in the eastern Pacific rise by 2, 3, sometimes 5 degrees Celsius above their normal values. This anomalous warming is El Niño. The consequences ripple outward in every direction. The warm water in the eastern Pacific heats the overlying atmosphere, shifting the patterns of rainfall and atmospheric circulation across the entire tropics and into the subtropics. Parts of Peru that are normally among the driest places on Earth receive torrential rainfall. Indonesia and Australia, normally wet, experience drought. The Indian monsoon is weakened. Hurricanes form in unusual locations. Droughts strike East Africa. Floods inundate parts of South America. For the marine ecosystem of the eastern Pacific, El Niño is catastrophic. The suppression of upwelling removes the supply of nutrients to the surface ocean. Phytoplankton populations collapse. The food web built on them collapses in turn. Anchoveta populations plunge, and the seabirds and marine mammals that depend on them starve. The Galapagos Islands, normally surrounded by cold, productive Humboldt current water, find themselves in the middle of a warm, nutrient-poor ocean. Populations of marine iguanas, sea lions, and penguins crash. The first people to give systematic attention to El Niño were the fishermen of Peru, who had known for centuries that every few years the ocean off their coast would warm, the fish would disappear, and the rains would come. They called this phenomenon El Niño, meaning the boy child or the Christ child, because it tended to arrive around Christmas. The opposite phase, when trade winds strengthen and the eastern Pacific cools further than usual, was later named La Niña, the girl child. The scientific understanding of El Niño developed slowly over the 20th century. The connection between the Pacific sea surface temperature patterns and the global atmospheric circulation was worked out by the British meteorologist Gilbert Walker in the 1920s and 1930s, though without understanding the oceanic mechanisms involved. Walker described a seesaw in atmospheric pressure between the western and eastern Pacific, which he named the Southern Oscillation. The combined phenomenon is now called ENSO, El Niño Southern Oscillation. Modern climate scientists can now predict El Niño events months in advance using a combination of ocean temperature measurements, satellite observations, and coupled ocean-atmosphere models. These predictions have real economic and humanitarian value, allowing farmers, water managers, and emergency services to prepare for the droughts and floods that El Niño reliably brings to specific regions. But the predictions are never perfect, because ENSO is an inherently chaotic system that is sensitive to small perturbations in ways that limit how far into the future useful forecasts can reach. In the Southern Ocean, encircling Antarctica, flows the largest ocean current on Earth. The Antarctic Circumpolar Current has no western boundary to constrain it. There is no continent in its path, nothing to deflect or block its flow. It simply circles the entire globe at latitudes between roughly 40 and 60 degrees south, driven by the powerful westerly winds that blow almost unimpeded around the southern hemisphere and connected by the Coriolis effect into a continuous, coherent current. The volume of water transporting by the Antarctic Circumpolar Current dwarfs every other ocean current. At its narrowest point, where it passes through the Drake Passage between the tip of South America and the Antarctic Peninsula, it carries approximately 130 sverdrups of water, more than 4 times the flow of the Gulf Stream at its most constricted point. Through its broader expanses, transport estimates climb considerably higher. The Drake Passage is the most turbulent stretch of ocean on Earth. The convergence of the Atlantic, Pacific, and Indian Ocean waters, the strength of the westerly winds, the powerful current beneath them, and the complex seafloor topography combine to create seas that have been the terror of mariners since the first Europeans rounded Cape Horn in the 16th century. Waves in the Drake Passage can exceed 20 meters in height. The expression Cape Horn fever was used to describe the psychological damage done to sailors by repeated exposure to these conditions. Before the opening of the Panama Canal in 1914, the Drake Passage was the only navigable route between the Atlantic and Pacific Oceans for large vessels. Ships carrying cargo between the coasts of the Americas, or making the journey from Europe to California during the Gold Rush, had no choice but to attempt the passage around Cape Horn. The attrition rate among ships and crews was substantial, and the cultural memory of the passage shaped maritime traditions for generations. The Antarctic Circumpolar Current connects the 3 major ocean basins in a way that no other current does. As it flows eastward, it draws water from the Atlantic, Indian, and Pacific Oceans into its circulation and mixes them together. It is the Great Connector, the ocean's equivalent of a global mixing bowl, and its existence is essential to maintaining roughly uniform conditions in the deep ocean worldwide. The current also plays a central role in the global overturning circulation. As Antarctic bottom water forms along the Antarctic continental shelf, where extremely cold and salty water sinks to the ocean floor, it flows northward along the bottom of all 3 ocean basins, carried partly by the pressure gradients created by the Antarctic Circumpolar Current. This densest and coldest of all ocean water masses fills the deepest parts of the ocean and slowly works its way back toward the surface over centuries, making the Antarctic Circumpolar Current not just a surface phenomenon, but a vital part of the global deep circulation. The biology supported by the Antarctic Circumpolar Current is extraordinary. The cold, nutrient-rich waters of the Southern Ocean are among the most productive in the world during the Southern Hemisphere summer, when constant sunlight drives explosive blooms of phytoplankton. These blooms support enormous populations of Antarctic krill, small crustaceans that are among the most abundant animals on Earth by mass. Krill are the keystone species of the Southern Ocean ecosystem, feeding on the phytoplankton and in turn being eaten by penguins, seals, fish, and whales. We have spent considerable time with the surface currents, the wind-driven gyres, the powerful western boundary currents, the productive eastern upwelling systems. But all of these movements are confined to the upper layer of the ocean, the top kilometer or so out of an average depth of nearly 4 kilometers. Below them, the deep ocean is also in motion, driven by forces that operate on timescales and at depths that make the surface currents look almost ephemeral by comparison. The thermohaline circulation, sometimes called the global ocean conveyor belt, is the planetary scale system of deep ocean currents driven by density differences created by variations in temperature and salinity. It is a circulation that moves water through every ocean basin, from the surface to the deepest abyssal plains, over timescales ranging from centuries to more than a millennium. A water molecule entering the deep Atlantic near Greenland today might not see the surface ocean again until it upwells somewhere in the Pacific or Indian Ocean more than 1,000 years from now. The engine of the thermohaline circulation operates at its most powerful in a few specific locations where the conditions conspire to produce water dense enough to sink to the ocean floor. The most important of these locations is the North Atlantic, specifically the Labrador Sea and the waters south of Iceland and Greenland. Here, warm and salty water carried northward by the Gulf Stream, and its extension gives up its heat to the cold atmosphere, cools rapidly, and becomes dense enough to sink in a process called deep water formation or convection. This sinking water is called North Atlantic deep water, and it is one of the dominant water masses of the global ocean. It fills much of the deep Atlantic and spreads southward along the ocean floor, eventually entering the Antarctic Circumpolar Current, which carries it eastward into the Indian and Pacific Oceans. Meanwhile, around Antarctica, an even denser water mass forms when sea ice grows in winter. As ice forms, it rejects the salt it cannot incorporate into its crystal structure, leaving the remaining water saltier and denser. This extremely cold and salty water sinks to the very bottom of the ocean, forming Antarctic bottom water, the densest water mass in the ocean. The sinking in these high-latitude formation zones draws warm surface water northward to replace it, which is why the Gulf Stream carries such a powerful flow of warm water into the North Atlantic. The thermohaline circulation is what ultimately sustains the Gulf Stream's transport, though the relationship between the two is complex and the subject of ongoing scientific research. The simple image of a single conveyor belt carrying water around the globe is a useful metaphor, but an oversimplification of the actual physics. The upwelling side of the thermohaline circulation, where the deep water returns to the surface, is more diffuse than the sinking side. Water upwells gradually across large areas of the ocean interior, driven by turbulent mixing that slowly dilutes the density of the deep water as it spreads and lightens. More focused upwelling occurs in the Southern Ocean, where the Antarctic Circumpolar Current and the prevailing winds create conditions that drive cold, deep water upward along the margins of the Antarctic continent, completing the circuit. The thermohaline circulation transports not just water, but also heat, salt, carbon dioxide, oxygen, and nutrients. Its role as a heat transporter is what most directly affects global climate. By carrying warm water to high latitudes in the Atlantic, it moderates the climate of northern Europe. By carrying cold water to the tropics in the deep ocean and eventually upwelling it, it slightly cools the tropics. The total heat transporting by the North Atlantic branch of the thermohaline circulation is comparable to the heat output of 1 million large power stations, a contribution to global heat redistribution that has no equivalent in any human-made system. The carbon transporting by the thermohaline circulation is of increasing importance in the context of climate change. As surface water sinks in the deep water formation zones, it carries with it the carbon dioxide dissolved from the atmosphere. This carbon is isolated from the atmosphere for centuries as the water travels through the deep ocean, making the thermohaline circulation one of the most important natural mechanisms for removing carbon dioxide from the atmosphere on century timescales. Changes to this circulation have the potential to affect how much carbon the ocean can absorb, with consequences for the rate of climate change. Ocean currents have shaped human history in ways that are rarely given sufficient attention. The great voyages of exploration that connected the continents and fundamentally transformed human civilization were not simply the products of courage and technology. They were made possible, and their routes were determined, by the patterns of winds and currents that explorers learned, often through painful trial and error, to use to their advantage. The Portuguese exploration of the African coast in the 15th century was governed from the beginning by the wind and current patterns of the eastern Atlantic. The explorers who tried to return from West Africa by sailing directly north found themselves fighting headwinds and adverse currents, making the journey slow and difficult. It was eventually discovered that the fastest route home from the South Atlantic was to sail far out into the middle of the Atlantic to the west, catching the southeast trade winds and the South Atlantic gyre's clockwise flow, then turning north and eventually northeast to catch the westerlies back to Portugal. This broad westward arc, called the Volta do Mar or Return of the Sea, was a crucial navigational insight that foreshadowed the routes Columbus would later follow. Columbus himself exploited the trade winds and the Atlantic gyre almost perfectly on his first voyage westward, though almost certainly without understanding the underlying physics. He sailed south from the Canary Islands to catch the northeast trade winds that blow westward across the tropical Atlantic, carried him to the Caribbean. On his return, he sailed far north before turning east, catching the westerly winds that blow back toward Europe at higher latitudes. The outbound and return routes formed a natural loop shaped by the gyre, a pattern that subsequent Spanish navigation in the Atlantic would refine into a well-established highway. The Manila galleon trade, which operated across the Pacific between the Philippines and Mexico for over 2 centuries from 1565 to 1815, was built entirely around the Pacific gyre system. The westbound route from Mexico to the Philippines used the trade winds and the North Equatorial Current, blowing ships westward across the southern part of the North Pacific. The eastbound return route, which took months longer, sailed north to Japan and caught the Kuroshio Current and the North Pacific Current, following the gyre's northern edge back to California before turning south to Mexico. This route, pioneered by the Spanish navigator Andrés de Urdaneta in 1565, was the first regular trans-Pacific route in history. The spice trade of the Indian Ocean was equally dependent on the monsoon system, which drives a seasonal reversal of winds and currents across the entire Indian Ocean basin. For roughly half the year, the southwest monsoon blows across the northern Indian Ocean from Africa toward India, driving a seasonal current in the same direction. For the other half, the northeast monsoon reverses both wind and current. Traders had exploited this reversing system for at least 2,000 years before the Portuguese arrived, building entire trading networks and seasonal schedules around the predictable rhythm of the monsoon. Arab, Indian, and Chinese merchants sailed with the monsoon in one direction and returned with it in the other, timing their voyages to arrive and depart in synchrony with the winds. The whaling industry of the 18th and 19th centuries created a vast body of practical oceanographic knowledge as captains charted the movements of their quarry across every ocean basin. Sperm whales follow the currents and the productive upwelling regions where their squid prey is most abundant. Whalers learned to find the animals by following the currents, and in doing so accumulated detailed records of current patterns, temperatures, and ocean conditions that would later prove valuable to scientists. The Nantucket whalers who advised Benjamin Franklin on the Gulf Stream were applying this practical knowledge to a specific problem, but their expertise was part of a broader tradition of ocean observation built up over generations of working the sea. For most of human history, ocean currents were known only through their effects: the deviation of ships from their expected courses, the unexpected appearance of warm or cold water, the arrival of tropical debris on northern beaches. Direct measurement was extraordinarily difficult. The ocean is vast, the currents are largely invisible, and the instruments needed to measure them were slow to develop. The earliest systematic current measurements were made by timing the drift of ships with their sails down and their engines off, comparing their actual position with where dead reckoning said they should be. This passive drift technique provided useful data, but was slow, spatially limited, and highly weather dependent. More direct measurements required instruments that could be lowered into the water and either hold position against the current, while measuring its speed and direction, or drift with the current while transmitting their position. The development of current meters, Instruments that measure the speed and direction of water flow at a fixed point revolutionized oceanographic observation in the 20th century. These instruments could be moored on anchored lines at specific depths and programmed to take measurements at regular intervals, building uptime series of current variability that revealed the complex, eddying character of ocean circulation that had not been apparent from sparse ship measurements. The discovery in the 1950s that deep western boundary currents existed, flowing southward along the western edges of ocean basins beneath the northward flowing Gulf Stream and its equivalents, came directly from moored current meter measurements that showed persistent deep southward flows where the surface current was heading north. Satellite oceanography transformed the field beginning in the 1970s. Satellites equipped with radar altimeters can measure the height of the ocean surface with extraordinary precision, detecting the subtle mounds and depressions created by geostrophic currents. Where the ocean surface is slightly higher than its surroundings, a current flows clockwise around the high in the northern hemisphere, counterclockwise in the southern hemisphere, following the same principles as a high-pressure system in the atmosphere. Satellite altimetry has produced continuous global maps of ocean surface currents since 1992, revealing the full complexity of the ocean circulation in ways that no combination of ship-based measurements could have achieved. The Argo program, launched around the year 2000, represented another revolution in ocean observation. Argo consists of a global array of around 4,000 robotic floats distributed across every ocean basin. Each float drifts at a parking depth of around 1,000 meters for most of its roughly 10-day cycle, then descends to 2,000 meters before rising slowly to the surface, measuring temperature and salinity throughout the water column as it ascends. At the surface, it transmits its data via satellite and then sinks again. Argo has produced an unprecedented view of the three-dimensional structure of the ocean and how it changes over time, providing a real-time global census of ocean conditions that previous generations of oceanographers could only dream of. Acoustic Doppler current profilers, which measure current speed and direction at many depths simultaneously by sending sound pulses into the water and measuring the Doppler shift of the reflections from particles moving with the current, have become standard equipment on oceanographic ships. Drifting buoys that float at the surface and transmit their positions via satellite provide direct measurements of surface current velocities across the global ocean. Underwater gliders, buoyancy-driven vehicles that can be programmed to follow specific trajectories and take detailed measurements for months at a time, have extended the reach of autonomous ocean observation. The picture that has emerged from all these measurements is one of extraordinary complexity. The ocean is not a smoothly flowing system of steady currents. It is turbulent, eddying, constantly changing. Mesoscale eddies, spinning vortices typically 100 to 300 kilometers in diameter and reaching from the surface to depths of 1,000 meters or more, are ubiquitous throughout the ocean. They contain most of the kinetic energy of the ocean and play a major role in transporting heat, salt, nutrients, and carbon across the large-scale current systems. Understanding their role in the overall circulation is one of the central challenges of modern physical oceanography. We come now to the question that casts its shadow over everything we have discussed tonight, and over the entire field of oceanography. What happens to ocean currents as the climate changes? How will the circulation that has maintained the conditions we take for granted respond to a warming world? And what consequences will that response have for the billions of people and the vast ecosystems that depend on these currents? The answers are uncertain in their details, but the general direction of change is becoming clearer. Several processes are already underway that will alter ocean circulation in significant ways over the coming decades and centuries. The most immediate concern is the potential weakening of the Atlantic meridional overturning circulation, the branch of the thermohaline circulation responsible for carrying warm water northward in the Atlantic and returning cold, dense, deep water southward. This circulation depends on the sinking of cold, salty water in the North Atlantic, but fresh water, which is less dense than salt water, inhibits sinking. And the melting of the Greenland ice sheet and Arctic sea ice is adding large and growing quantities of fresh water to the North Atlantic, precisely in the regions where deep water formation occurs. Measurements and proxy records suggest that the Atlantic overturning circulation has already weakened over the past century, and climate models consistently project further weakening as the century progresses. A significant weakening would reduce the transport of warm water into the North Atlantic and reduce the release of heat to the atmosphere over northwestern Europe. Paradoxically, some of the regions most threatened by global warming might actually experience cooling, or at least a reduction in the warming they would otherwise experience as the ocean's heat pump slows. A complete shutdown of the Atlantic overturning circulation, sometimes sensationalized in popular culture as a sudden catastrophic event, is considered unlikely in the near term by most climate scientists, though not impossible on longer timescales if greenhouse gas emissions continue unabated. The circulation has shut down before in Earth's history, during periods of rapid ice sheet collapse at the end of ice ages, with dramatic consequences for climate across the North Atlantic region. Understanding the stability of the current circulation and the conditions under which it might tip into a fundamentally different state is one of the most urgent questions in climate science. Changes to the surface wind patterns associated with climate change are also expected to alter the surface circulation. The strengthening and poleward shift of the westerly wind belts, which climate models consistently project in both hemispheres, will change the position and intensity of the subtropical gyres. The Antarctic Circumpolar Current is expected to strengthen as the westerlies in the southern hemisphere intensify. Changes to the monsoon circulation will alter the seasonal patterns of the Indian Ocean currents. Coastal upwelling systems, which support some of the most productive fisheries in the world, are expected to intensify in some regions as the winds driving offshore Ekman transport strengthen. But warmer surface waters will also cap the upwelling more effectively, reducing the temperature contrast and potentially limiting the nutrient supply to the surface, even as the physical process of upwelling continues. The net effect on productivity is uncertain and likely to vary by location. Ocean warming itself changes the properties of water in ways that affect circulation. Warmer water is less dense and therefore less inclined to sink, reducing the vigor of convective overturning. Warming also reduces the solubility of gases in seawater, meaning that a warmer ocean holds less dissolved oxygen and less dissolved carbon dioxide, affecting both the marine ecosystem and the ocean's capacity to absorb carbon from the atmosphere. The rate at which the ocean is absorbing heat from the global warming already occurring is extraordinary. The ocean has absorbed more than 90% of the excess heat trapped by increased greenhouse gases over the past several decades, a figure that underscores both the ocean's immense thermal capacity and its fundamental role as the primary buffer against atmospheric warming. But this absorption has not been without cost. The energy stored in the ocean must eventually be redistributed, and the patterns of that redistribution will shape regional climates for centuries. We have traveled a great distance tonight. We began at the surface, where the wind first sets the water in motion, and we followed the currents around the great subtropical gyres, through the powerful western boundary currents and the productive eastern upwelling systems. We visited El Niño in the Pacific, the Antarctic Circumpolar Current in the south, the thermohaline conveyor in the deep. We sailed with the navigators who learned to read the currents and followed them around the globe. We watched scientists learn to measure and map what the eye cannot see, and we considered the changes that are already underway in a warming world. What emerges from all of this is a picture of the ocean not as a passive body of water, but as an active, dynamic, deeply interconnected system. A system that regulates climate, distributes nutrients, shapes ecosystems, and mediates the exchange of heat and carbon between the ocean and the atmosphere. a system whose invisible rivers have been flowing for millions of years, and whose future depends in significant part on choices being made right now. The ocean does not advertise its importance. Its most consequential processes happen far from sight, in cold, dark water moving at centimeters per second along the deep ocean floor, or in the slow upwelling of nutrient-rich water off a distant coastline, or in the barely perceptible cooling of warm Atlantic water as it approaches Iceland and begins its long journey back toward the abyss. These are not dramatic spectacles. They are quiet, patient, and enormously powerful. To understand the currents is to understand, in some fundamental sense, how the planet maintains itself. The conditions that allow complex life to exist, the relatively stable climate, the moderately distributed temperatures, the cycling of nutrients through the water column and back to the surface, all of these depend on the ocean's circulation continuing to function as it has throughout human history and long before. If you are still listening, still present, still drifting along with the current of this long night, then thank you. The ocean is patient with those who take the time to understand it. It has been flowing since long before the first human looked out over it and wondered what lay beyond the horizon, and it will continue flowing long after the last question about it is asked. Let the currents carry you now, cold and dark and slow and vast, moving through the deep in the darkness, carrying the heat of the tropics toward the poles, returning the cold deep water to the light. Somewhere in the Pacific, water is upwelling that last saw the surface centuries ago. Somewhere in the North Atlantic, warm water is giving up its heat to the cold air and beginning its long descent. The ocean is, as it has always been, in motion. Sleep well, we will be here when you wake.